Hi, and welcome to this lecture on chemical bonds. So we're going to dive down into the details now about how and sort of why the different atoms will sort of stick together and make these molecules and compounds that we've been talking about for months now. And we're in a position to do that because we have looked at the periodic table and studied electron configuration. We now know where the electrons are living. We have always known how many there were. And now that we understand kind of orbitals and the shapes of orbitals and some of that geometry, we can start understanding how they sort of exchange and share electrons and why the different atoms will do different things. So first of all, just some definitions here. When we're talking about a chemical bond, that we're talking about this force that's keeping the atoms together, right? And that can either be a really strong force, in which case it requires a lot of energy to break that bond. That would be a strong bond, right? And or the atoms could be sort of loosely attracted to each other, and they can be held together by weak forces, and in which case it does not require a lot of energy to break it apart, and that would be a weak bond, right? And so what is the bond? When we're talking about chemistry, we're always talking about electrons and the nuclei, the atoms involved, and it really is just as simple as the attraction of the negative charge, that is the electrons that are in the bond, for the nuclei, the positive charge, of course, being in the nucleus. So it's that negative attracting on positive. That is the bond, the chemical bond. So we have a picture here, and we'll come back to this picture of water, right? So what we're doing is we've known for a long time, how to read a chemical formula like this. This means that we have two hydrogen atoms and one oxygen atom that are somehow like globbed together to make a molecule of water. And so now we're going to look at the details and say, like, well, how is it that they are actually stuck together? And the answer is, right, in this case, is that there are these shared electrons in between the positive nucleus of the hydrogen and the positive nucleus of the oxygen. And this would be the chemical bond between hydrogen and oxygen. And then, of course, there's a second hydrogen. So we have the same bond happening over here, right? And why does it look like that? And why is it shared that way? It really has to do with electron configuration, and we'll come back to that. So I want to remind you about something, and this turns out to be really relevant for bonding also, is in the last unit we talked briefly about ionization energy, and that is, how much energy does it require to come and pull that valence electron off, right? And so if the electron is all by itself on the outer shell, right, and it's really far away from the nucleus, then it's hardly held in there at all. That would be like the atoms down here in the bottom left. And that would not require a lot of energy at all, right? Because that atom is barely holding on to those electrons because they're so far away, and the positive charge is so screened off by all of those electrons in the shells below them. On the other hand, in the upper right here, right, you have an electron. The last valence electron is in an incomplete shell, right? And can see the nucleus is well attracted to the positive charge beneath it. And is not that screened off or anything like that. And so it requires quite a bit of energy to pull those electrons off, right? So the ionization energy trends, as you see on this, are right, low ionization energies in the bottom left and high energies in the upper right. And this is, of course, related. This is how it's related to bonds. We've already talked about this. That's why the guys on the left-hand side, right, the elements on the left-hand side, the metals, tend to lose electrons and become positively charged, whereas the nonmetals over here on the right-hand side, they tend to gain electrons and be negatively charged. It's really related to this ionization energy, but we're going to recharacterize it in a minute. So if you have a case where there's a really big differential, right? One guy, you have a metal that is really easygoing to take his electron away, and then you have a non-metal that is really kind of desperate for an electron, then you can have this complete transfer of electrons. And I think this is the kind of language that I've used with you before, because I think this is one of the kind of the simpler bonds to understand. And this is called an ionic bond, right? This is not all of the bonds. This is one extremal case where the electron, one atom winds up completely without the electron, right? So this is table salt, and the sodium becomes positive because he's short an electron. Now, where did that electron go? Went to the chlorine, who now has the extra electron, the purple one you see here in the chlorine. And so now the chlorine has more electrons than protons, so it is negatively charged. So this is the classic case when we were doing the figuring out the molecular formulas and the compound formulas. We'd figure out whether you needed 2 or 3 of each atoms to go with the other one. This was the game we were playing. And this is the pictures that you should have in your mind, right? Is the electron actually has gone completely off and then the other ones. And so in this case, the bond is actually the entire atom being positive and the entire other negative atom being negative, and that's what's pulling them together, right? And if you're picturing a solid, an ionic solid, right, that attraction kind of goes throughout the solid, right? So they tend to be pretty strong bonds where they're connected pretty well all the way across the material. Now, the other type of bond is a shared situation, right? So in the ionic, you would not say the electron is shared. One guy lost it and the other guy gained it, and they're just overall attracted because of their overall positive and negative. The other solution would be when they're fighting over the electron, it's kind of even-steven, right? So think about the H2 gas, right? This is one of our diatomic gases, and this would be true for all the diatomic gases. If you have two of the same atoms and they're meeting, it's not like one is going to pull the electron more than the other one. And so where does the bond come in? The bond comes in because they share them, right? And so each hydrogen is coming in with one electron. And so what you can picture the H2 molecule as being is the two hydrogen nuclei like this, and the total two electrons that they bring to the party, right? In general, we only worry about the valence electrons. So in some of these pictures, we don't even show the inner electrons. For hydrogen, of course, there is only one shell, and so the valence electron is the totality of it. And so here are the two electrons, and now you don't think about, and the molecules don't feel like the electron belongs to either atom anymore. They're both shared. And that's the bond. This is called a covalent bond, when the electrons are hanging out and they're sort of equally shared between the two. They're attracted to the positive charge on either side, and that's what's holding the whole molecule together, right? So ionic bonds, there are no shared electrons. The electrons were transferred. And in covalent bonds, the electrons are shared, and the bond is actually those shared electrons in between the two nuclei. Now, obviously, these are two extremal cases, right? One is a complete transfer of the electron, and the other one that I've shown you is a complete 50-50 sharing of the electron where everything is equal. The reality of the situation, of course, is that most bonding are going to be somewhere in between, right? And so it's a continuum of which ionic bonding and this even pure covalent, they call it, are on either ends of the spectrum. When you are hooking up covalently bonded, people that are sharing electrons, but they're not the same element, then one of them is going to sort of have an overall need for electrons, or an affinity for electrons is what they say, and more so than the other one, and then they're going to hog the electron a little bit, and it won't be a completely even covalent. Those are called polar covalent bonds, and the polar indicates that there is there is an imbalance in the charge, right? And that's what these delta, this little scripty thing is a lowercase delta sign. And so this delta plus and this delta minus are indicating that you have partial charges. In other words, it's not like one where the positive charge is not short an entire electron and the negative side has not gained an entire electron. That would be like the ionic case in the far left. What you have here is you have the shared electrons are spending time near both nuclei, but the shared electrons are spending a little bit more time, or the overall electron density really is kind of a better way of thinking about it, is a little bit greater around the atom on the right in this picture and a little bit less around the atom on the left. So there's sort of an emergent positive charge because it's less than being short an entire electron, but it is not neutral anymore, right? The overall molecule is going to be neutral, just like in the overall ionic, if you include both atoms. The overall is neutral. Here, the delta positive should be the same as the delta negative because the total number of electrons and protons within that molecule are the same, but the sharing is uneven, right? Now, how do you decide how to share? And the answer is, this is kind of related to ionization energy, but the affinity for the electron, for the atom or the element, the affinity is the reverse of the ionization energy, which is how badly does it want the electron. But it follows that trend for ionization energy in that, in the upper right over here, ignoring the noble gases, right? Because the noble gases are kind of fat and happy and they don't really participate a lot in chemistry, especially not every single one. You can see the ones in color here will undergo chemical reactions. But in general, right, these guys on the far right, they have complete outer shell, valence shells. And so when they bounce around, they don't participate in chemical reactions very much because they don't tend to give or receive. And so you don't really count them for electronegativity, the white ones, the white squares here. But in general, over here, the guys that are just missing one, they they have a high electronegativity because they really have a high affinity to hog the electron. Because, you know, if you're in column 7A here on this chart, you're just lacking one electron. So if you could just have that one electron around you, you get a complete shell. Everything can be symmetric, you know. And in 6A, if someone would just give you share 2 with you, then you really want the 2, and you tend to hog them, basically, right? And so you would get that delta minus sign on that polar molecule. On the other hand, the story is the opposite on the right-hand side. Right? On the right-hand side, these guys have low electron affinity, right? Which makes sense because they have low ionization. They're quick to give up their electron. And therefore, when they participate in a covalent bond, they have low electronegativity numbers, right? You can see numbers down like here. The lowest one is down here in the bottom left, which is 0.7. And the highest one's up here for fluorine, which is close to 4. So that's the range of electronegativities, like somewhere between 0.7 and 4, with the higher number meaning, yes, I really do want the electron to myself, thank you very much. And the lower one meaning like, I kind of want the electron, but not as badly. And so what you want to look at in any compound is the difference between those two numbers, right? So if the two numbers are the same, then you get a pure covalent bond and they share 50-50, like the first picture I showed you with hydrogen. And if the numbers are really, really different, then you're going to get an ionic bond, you know, and the cutoff is somewhere around 2, say. So if the difference in electronegativity is somewhere around 2 or higher, of course, then you think of one guy's completely getting rid of the electron and the other guy completely owning it, and you would consider that ionic bond. If the electronegativity difference is 0 or a really small number, like, you know, 0.1 or 0.2, something lower than 0.5, I think might be a reasonable cutoff, then you would consider that a pure covalent bond, and it's pretty close to 50-50. Remember, everything is a continuous spectrum, and so you know, we're putting things in the bins and we're assigning numbers, but the cutoffs are kind of soft, and that should make sense to you because it's not an either-or situation, right? The electron is around, and you know, it may spend 99.9% of its time over here. So then would you say it's transferred over there? I would say yes, but you know, you can make an argument that, well, there's still 0.1% chance of seeing it over here. Okay, so the nonpolar covalent bond, I think I already talked about this with the other slide, right? The fact that, so here's hydrogen chloride, right? The Cl is in the upper right, so it has high electronegativity. The hydrogen has lower electronegativity. We can look at the numbers over here, right? It's a 2.7 versus a 3 point something. I can't quite read it, right? But it's definitely, the chlorine's a little bit higher. And so the chlorine is going to take the shared electron pair, and it will be spending more of its time closer to the chlorine. So the chlorine overall has more electrons than protons, not by a whole electron, but you know, the overall negative exceeds the overall positive on the right-hand side of this picture, so we get a delta minus over here. And then over here on the hydrogen, the single proton in hydrogen and the shared electrons are kind of a little bit farther away from it, and so it has an emergent overall delta plus, right? And so this nonpolar covalent bond, just because of the way the electrons are shared by itself, leads to molecules that have kind of a positive end and a negative end, which is super important with how that molecule interacts with its environment and other molecules. What that's called is a dipole moment, right? When you have an object that is not charged, but the charge distribution is uneven such that one side is positive and the other side is negative, we call that a dipole moment, right? So it will respond to other charged particles even though it's neutral because it has these partial charges, right? And the tradition from physics is to always show electric fields going from positive to negative. So that's what we do in dipole moments, is we will draw a little arrow to indicate the direction of the dipole moment. The arrows, by definition, go from the positive side to the negative side. And that's just a generally true thing in science that we show in electricity. We show arrows going from positive to negative. And there's a lot more to be said about that, but just introducing the term for today. So how many electrons do the different elements, how many will they share? How many bonds will they like to form? Like, why is it H2O and not just HO? And the answer really is about electron configuration. And the answer that I'm always talking about in terms of completeness, it has a name. It's called I was taught the Octet rule. In the book, I noticed it's called the noble gas rule. Of course, it means the same thing, which is that the elements are going to share and transfer electrons in such a way that they have a complete outer shell, right? And if the shell that their valence electrons are in is mostly empty, right, they only have a few electrons, so in other words, they're on the left-hand side of the periodic table, then they tend to shed them down to the noble gas configuration that's just underneath, right? So they have the complete lower shell, their inner electrons. On the other hand, if you're on the right-hand side of the periodic table, you have a mostly full valence shell. And so the easier thing is to gain a few electrons to get to the noble gas to complete. So to get to the noble gas configuration at the end of your row, if you will. So let's look at this example. This is carbon dioxide, CO2. And what you can see is that the red here is the oxygen. What does the oxygen bring to the party? Well, here's the electron configuration. It's basically a helium configuration with a 2s2 and a 2p4 on the top of that, right? So if you think about that, the oxygens are looking for, what would they need? They would either need to shed kind of all 6, or they would like to gain 2, right? But they're probably not going to do either if they're with a carbon, because it's not like a metal, non-metal situation. So they're going to get covalent bonds, right? These will be slightly polar covalent bonds, but they'll be covalent bonds in that the electrons will be shared. And so how many will they share? Well, the oxygen wants 2 more electrons. And now it looks at the carbon. The carbon has the helium and then a 2s2 and then a 2p4. So he's short 4 electrons to get to that complete noble gas configuration, right? 2s2, 2p6. That 2 plus 6 is where the word octet for 8, this is not 8 comes in. And so if you look, if they will share 4 electrons, it all works out, right? So all the black dots are the valence electrons. That's the S2 and the P2, right? So those 4 here. And then the red is coming in with the 2s2 and the 2p4. There's the 6 reds that are coming in with each oxygen. And so you get a situation here where the carbon is going to share 4 electrons with this oxygen. The carbon contributes 2, and the oxygen contributes 2. That's something that's known as a double bond. We'll talk about that later. And of course, the other oxygen is doing the same thing. And now if you look at it, each element is happy here in the sense that their octet rule or their desire for the noble gas configuration is satisfied. And that really is what drives chemistry. That's what drives the atoms to bond in the way they do and to bond in the numbers that they do, right? And if you go back to our original example here that I showed you, the H2O, you can see what's going on here is they put the electrons in rings that correspond to the s and the p orbitals, right? So oxygen has its 1s2 down here, and then the second energy level, or the fact that we find it on the second row, means it's going to have its valence electrons there, and they are the dark blue ones, right? So they say lone pair here, so that would be like maybe their 2s2 electrons, and then they have 4 in the p orbital, so there's 2 together, right? Spin up and spin down. And then there's 1 sitting by itself in 1 p orbital, and then 1 sitting by itself in the 3rd p orbital. And so those are the guys that are unpaired. And then when the hydrogen comes in, the hydrogen just comes in with its 1 unpaired electron. And so 1 hydrogen will pair off with one of those unpaired p orbital electrons in oxygen, and the other hydrogen will do the same. And now by sharing like that, they all have that feeling of completeness, right? Because for hydrogen, since it's in the first row, it's not really the octet rule. That's why maybe they like the noble gas rule is better, because if you're in the first row of the periodic table, you're filled with only 2, right? You're not looking for 8. So I like this picture because it kind of gives you a good view of the overlap and the intersection of electron configuration and covalent bonding. Okay, I think that's a good enough introduction to the overall ideas and a lot of vocabulary there. There's more to unpack, of course, and we'll do that on another day. All right, thank you.